So what we're going over today, guys, is the law of conservation of energy. Now, we've talked about it before, okay? On the very first day, we talked about what the law of conservation of energy says. Energy can't be created, it can't be destroyed. If you do work on something, it can gain mechanical energy. If it does work on something, it will lose mechanical energy. All of that is part of the law of conservation of mechanical energy, right? So what we're going to do today is review what mechanical energy is, and then start looking at some situations in which energy is conserved. Now, those situations are all going to be in what we would consider to be the perfect physical world where there is no what? Friction. There's no friction. Okay? So basically, in every one of these situations, all of the initial energy will be there at the end. Okay? None of it will be lost to non-conservative forces like friction. There will be no work done. Okay? Because if work is done, then the initial energy and the final energy are different. Okay? So we're only dealing with situations where energy is completely conserved and no work is done. Okay? Realistically, there aren't any situations like this in the real world. Okay? There's always going to be energy lost to work being done against other things. It's not actually all that hard to deal with that, but we're just going to look at it kind of from a simplistic point of view. Okay? So first thing we got to do then is talk about what mechanical energy is. Okay? Mechanical energy is the sum total of your kinetic energy and your potential energy. Okay? It is your total mechanical energy. That is the sum of both your energy due to movement and your energy due to position. And in even more complex situations, any other forms of mechanical potential energy, like elastic potential energy. Okay, so if I had, for example, let's say like a roller coaster, okay, like this, and the roller coaster cart was up here, and it was on a compressed spring, okay, it would not only have gravitational potential energy because it's above the ground, but it would also have elastic potential energy because it's being pushed onto a loaded spring. Okay? When it gets down here, all of its energy will be kinetic. Okay? And that kinetic energy down here will equal all of the energy it had up here. Okay? Gravitational plus the elastic potential. Right? We're only going to deal with gravitational and kinetic, but just so you understand, all types fit into mechanical. Okay? All right, so when energy is transferred to an object, it can cause a change in both kinetic and potential energy simultaneously. It's important to understand that. Okay? If I throw a rock, okay, and I throw it slightly upwards, it is going to gain both potential as well as kinetic energy because of what I have done. Okay? So it is possible, like I say, to change both at the same time. Okay, since kinetic and potential energy are so closely related, we usually just refer to them as one thing. Okay, certainly mechanical energy is broken up into the two parts, but we consider them to be one because they often act together. All right, everybody okay with that? Okay, do we have a formula for EK? All right, 1/2 mv squared. Right, we've already used that. We know how it works. We have a formula for EP. It's mgh. How hard is it going to be to calculate the total mechanical energy of an object? Not hard. All we have to do is use those two formulas and add them together. Okay, it's really not hard. All right. So looking at example number 1 here. Okay, I got a 0.30 kilogram baseball thrown in a straight line through the air at a height of 2.50 meters above the ground. Now, is it actually possible to throw a ball in a straight line? No. Okay. Nothing moves in a straight line in the real world because of gravity. Yeah, gravity makes everything arc. Okay, so it's above the surface of the Earth. It's moving at 20 meters per second. I want to calculate its total mechanical energy. So mechanical energy is kinetic plus potential. Kinetic energy is 1/2 mv squared. Potential is mgh. I just plug in my numbers. So the kinetic is 1/2 times the mass, 0.3, times the speed squared. Okay, so 20 squared. Plus 0.3 times 9.81 times 2.5, okay, is the height of the ball. So in this situation, which one's the bigger part of mechanical energy, the kinetic or the potential here? Yeah, the kinetic is a way bigger part, right? I mean, you think about it, it's moving at 20 meters per second, and that number has to be squared. This number is way bigger than that number is. Okay, it has way more kinetic energy than it has potential. All right, so 60 joules versus 7.36 joules worth of potential gives me a total mechanical energy of 67.4 joules worth of energy. Okay, worth of mechanical energy. Everybody all right with that? Easy peasy? Okay. Then I want you guys to try 8, 9, and 10. Okay? Now, the correct answers are here. 97.89, 1091.8, not to the right number significant digits because I was obviously in a terrible hurry. Okay, but those are the answers there. These are answers to something I'm going to ask after. Okay, so don't worry about these two numbers here in red. Okay, I'm going to ask about those after. Right now, I just want you to try 8, 9, and 10. Okay, I'll go over number 8 in a minute, and we'll go over number 9. Okay, so for number 8, we have this seagull flying horizontally at 8 meters per second. So they have kinetic energy. Okay, they're carrying a clam that has a mass of 300 grams, but our mass always needs to be in kilograms. Okay, and we want to calculate its total mechanical energy when it is 30 meters above the ground. All right, so mechanical energy equals EK plus EP. All right, so that's going to be 1/2 times 0.3. Okay, 0.3 kilograms times 8 squared. That would be our kinetic energy plus 0.3 times 9.81 times 30 meters. All right, and when we do that, we should get 97.9, and that actually has the right number of significant digits in it, 97.9 joules. Okay, now, before we look at 9 and 10, something I want to ask you here. We've been working on these kind of questions. Work equals a change in energy, whether it's kinetic or potential. Are these still examples where energy is conserved? Okay? In every one of these questions, like some of the contexts were, I pull back a bow and arrow. I do this much work. How fast will the arrow leave the bow? Well, we always assumed that all the work I did in drawing the bow was going to become kinetic energy for the arrow. Does that mean the energy was all conserved? Yes, it does. Okay? In a work energy theorem question like the ones we've been doing, certainly we've been changing the energy of part of a system. Okay? But the energy of the system was always conserved. So the bow and arrow, two separate objects, are still part of a system. When I put energy into that system by doing work, that energy will be conserved within the system. Okay? It's going to move from the bow to the arrow, but it's all still going to be conserved. Everyone kind of follow me there? Okay. How many people have done number 9? Okay, so we need a few minutes on number 9? Yep. Okay. Okay, yeah, but we don't want to get into, look, I tried like 5 different things, and this one last thing that I tried got me the right answer, because that won't work on a test. You don't have the right answer in front of you to do that with. You can't guess and check on a test. So, here's what we need to think about. We were told that mechanical energy is the sum of kinetic plus potential. Everybody okay with that? Okay. They're telling us it has 3,000 joules. Yeah, 3,000 joules of kinetic energy, or of mechanical energy, and it's telling us how fast it's moving. So I have this number, and I can calculate this number. It wants to know the gravitational potential energy of the athlete. So what do I do with this? I just subtract it over here. That'll get me the potential energy, won't it? Yeah. Okay, so if kinetic plus potential equals mechanical, then mechanical minus kinetic should equal potential. Right? Okay. So you definitely don't want to overthink it. All right, so that's going to be 3,000 minus 1/2 times, what was our mass here? 55 times 8.33 squared. All right, so the athlete then, okay, so the athlete has 1,091.8 joules worth of potential energy. Now, I would not have asked the question that way. I would have asked it this way. Instead of asking you how much potential energy the athlete has, I would ask you how far above the ground they are.
So you have to calculate, you have to find mechanical, you have to find the height.
Well, actually, you don't. You could just do this. Instead of solving for EP, you could write the formula for EP. And instead of solving for all of this, you could just bring that over and solve for h. Everybody follow me there? Okay? It's really not all that much more to do. It's just instead of solving for the entire energy type, you're solving for one part of that energy, which is the height. So if I do that, okay, I'd very quickly be able to calculate what the height of the athlete is, okay, by taking that 1,091.5 or 0.8, sorry, and dividing it by 55 times 9.81. Right? They're 2 meters off the ground. In terms of high jump, that's pretty good. Okay, I coached track and field for 20 years, and I can count the number of times on one hand, and I've seen somebody go over 2 meters in high school. Okay, it's impressive. Okay, because 2 meters, guys, is 6.5 feet. Okay, so yeah, they're jumping over a 6.5 foot person. Okay, all right. Number 10, very similar, except this time it's asking you to calculate the kinetic energy. Okay, so give that one a try. You'll probably do that one a lot faster now. Okay, so looking at number 10 here. Okay, construction worker drops a 2 kilogram hammer. So we know the mass is 2 kilograms. Okay, and we know that it's 50 meters above the ground, and its mechanical energy is 1,880 joules. Right? So from that we need to calculate the kinetic energy of the hammer. So we're looking for EK, which means we have to do what with EP? We have to subtract it. All right, so we're going to take EM minus EP equals EK. All right, that's how this question, as it's stated, would be solved. And we would just write in our 1,880, okay, minus 2 times 50 times 9.81, okay, and that would give us our 899 joules. All right, that'd be fine. Everyone okay with that? Yes. All right, but I asked you, in addition to that, to calculate how fast the hammer would be going. So now I'm going to say 1880, sorry, minus m times g times h, so that'll be our 2 times 50, I shouldn't have erased all that, times 9.81 equals 1/2 mv squared. I want to get v, so what do I do with the 1/2? Divide it, same with the m, right? And then I square root. Okay, that'll give me v, right? It's one extra step, but it's very much like we did in the work energy theorem problems. Okay, so when I do that, then I would get the speed of the hammer. So 899, I'm just going to shortcut here, guys. So square root of 899 divided by 0.5 times 2.
It's just
189, yes. Yeah, okay. So be moving at 30 meters per second. Okay. Everybody all right with that?
Yes, sir.
Okay. Okay, so I want to look at these examples here because they combine work energy theorem with conservation of energy. So I use an average force of 100 newtons, and this was important from yesterday's lab. Okay, if you recall, we had these graphs yesterday from they were force versus distance graphs. And it was always talking about the average force, the average force. Well, that's because as I pull back anything, a rubber band, a bow and arrow, okay, the force I have to use increases with distance. So we're using the average force, okay, in order to calculate what? This might help with your lab. If I'm taking the average of this and multiplying it by this, what does that calculate? Good. Okay, so if I take this 100 and I multiply it by 0.5 meters, how much work have I done? 50 joules. Okay. So I do 50 joules worth of work in drawing back the bow. How much potential energy is in the bow?
50 joules.
50 joules. Requires no calculation beyond what you've already done. Law of conservation of energy and work energy theorem go together. If I do 50 joules worth of work, that energy has to stay there. It can't be destroyed. Okay? It's not doing work on anything because it's stored in the bow. Everybody follow? Okay. If I let the bow go, how much kinetic energy will the arrow have? 50 joules. Law of conservation of energy. It can't be created. It can't be destroyed. It can be transferred. It can be changed from one form to another, and it is, but the number of joules remains the same throughout all of those conversions in the perfect physical world. In the real world, not the case. Okay? I let that bow and arrow, I release that bow, and I can hear the string, Okay? There's going to be some heat generated in the bow. All of those are going to represent places where energy will go that's not into the arrow. Will the arrow get the vast majority of the energy? Probably. Okay? But I'm still going to lose some. All right. If I aim the bow and arrow straight up in the air, what will be the maximum gravitational potential energy of the arrow? 50 joules. Guys, it's still a system. Okay? I did 50 joules worth of work. The bow does 50 joules worth of work on the arrow. The arrow has 50 joules worth of kinetic energy and goes straight up in the air until it gets to its maximum height where it stops, and all of its energy is now potential. All of it is 50 joules. Same amount of work that I did in drawing back the system in the first place. Okay? Then when it comes back down, get out of the way, because it'll have 50 joules worth of energy when it comes back down. Okay? And again, the perfect physical world. In the real world, that arrow is not going to fall straight back down. It's going to tumble, and it's going to lose energy because it tumbles, okay, and things like that. But in the perfect physical world, it would fall right back down at 9.81 meters per second squared. It'd be very dangerous, okay, when it came back down. All right? Okay. So, law of conservation of energy is kind of what we just talked about here. Once energy is in a system, it stays there unless that system does work on something. So if I drop something, okay, so if I'm holding this pen right here, what kind of energy does it have right now? Okay, if I drop it, when it hits the floor, the instant it hits the floor, all of that energy will be kinetic, but it'll all be conserved. If it has 100 joules worth of energy here, when it hits the floor, it has 100 joules worth of energy. Okay, and I'll know that because when it hits the floor, it'll make sound. And it'll bounce around a little bit, make more sound, and eventually it'll stop because all of the energy it had will have been turned into sound and heat and denting the floor. Okay? Everyone okay with that? All right, so in this example problem here, okay, this is about as simple as a law of conservation of energy problem can get. I have a 1.5 kilogram rock. Okay, so I know the mass. Okay, it's dropped over the edge of a cliff. So if it's dropped, its initial velocity is, okay, and the cliff is 30 meters high. Okay, so its initial height is 30 meters. Okay, we're looking for the speed of the rock as it strikes the surface of the lake. What's its final height? 0. Okay, so we're looking for VF. Okay. So here's the first thing we know. Because this is a law of conservation of energy question, EI equals EF. I know it's a law of conservation of energy question because there's no mention of any what being done. No work. Okay? There's no forces, nothing. The only thing going on here is gravity pulling something from a height to the ground. All right, so that means my initial mechanical energy will equal my final mechanical energy. Everybody all right with that? Okay, how do I calculate mechanical energy? What two things do I add together? Right, potential and kinetic. So I'm going to say my initial potential plus my initial kinetic is going to equal the same thing on the other side, but final. Okay, we said mechanical energy is the sum of kinetic and potential, so that's what it looks like in terms of final and initial. Okay, those energies are the same. Now, looking at the context of this question, do I actually have all four forms of energy here? Because initially I'm dropping the rock. So initially, what type of energy do I not have? I don't have any kinetic. At the end, my height is 0, so I don't have any. Right. All right. So now, I'm still saying my initial mechanical equals my final mechanical. I'm just saying I don't have any initial kinetic or any final potential. Okay? So, do I have a formula that'll calculate this number? Formula for that one? Okay, so can I calculate how fast it's going?
Yes, sure.
What am I solving for? VF, right. So what do I do with the half of m? Divide it. What happens? Yeah. Is that strange? Actually, it's not. It seems strange right now, but I'll tell you why it's not. All things in the perfect physical world fall at the same rate. They would all be going the same speed when they struck the lake, whether it was that little rock or a bowling ball or a feather or a brick, it doesn't matter. In the perfect physical world, all things fall at the same rate, 9.81 meters per second squared. Obviously in the real world they don't do that, okay? But we're not dealing with the real world. In fact, I'll show you a video where they make a bowling ball and a feather fall at the same rate. It's really cool actually. Okay, so I've divided both sides by half of m, and then I need to take the square root. So that gets me VF. So now I plug in my numbers. I've got 9.81 times the initial height, which was 30 meters, divided by 1/2, square rooted. That'll get me VF. Okay, so 9.81, oh, not 98.1, 9.81 times 30. Okay, times 2, because that's what dividing by a half does. Okay, and then square root that. All right, so that rock, when it strikes the lake, will be moving at 24.3 meters per second. Whoop, that's supposed to be meters per second. Okay, everybody all right with that idea? So all we did was say energy's conserved, so initial and final are equal. Here's what our initial and final are made up of, and we crossed off any ones that were 0. Then we put in their formulas, we manipulated and solved. Okay.
Will there be questions like if the rock is in the lake and is going down?
No. No. Physics 20? Yes.
Oh.
But not in science. All right, I'll show you that video I was telling you. So given what we just did with the rock being dropped off the cliff, I want you guys to see if you can solve these two. So it's just like the rock, okay? And we're dropping a water balloon this time from a height of 12 meters. Calculate the speed just as it hits the ground, okay? And then the other one, a child on a trampoline is jumping vertically into the air with their initial speed being 1.6 meters per second. Calculate how high they will get, okay? So the answers are here. You can see if you did it right. But remember, this time we are dealing with a situation in which mechanical energy is conserved. Okay? I'll give you a few minutes on those. So for number 11 here, all right, we've got initial mechanical equals final mechanical. So we always want to write out that means, or essentially expand it out. Okay, so that means the initial potential plus the initial kinetic equals the final potential plus the final kinetic. Okay, at this point we want to eliminate any energy forms that actually are 0 joules. Okay, so in other words, we don't have them. Since this object is being dropped, that means that initially I have no kinetic energy. My other reference point is ground level, which means I have no right, and that's at the end, so I have no what? I have no final potential energy. Okay, if my final height is 0, I have no final potential energy either. Right? That simplifies things. Now I can simply say that my initial mechanical is all potential and my final mechanical is all kinetic. Okay. Now I want to expand that out again. I want to put in the formulas for each of these. M times G times H initial equals 1/2 times M times V final squared. And I'm looking for V final. So I need to get VF by itself, so I'm going to divide both sides by half of M. The M's will cancel, and then I'll take the square root. All right, so that'll be G times H initial divided by 1/2, okay, equals VF, okay, which will be 9.81 times 10 divided by 12.
I thought you just divided.
Sorry, not by 12, by 1/2.
Yeah.
Oh. And I know I did 98.1. I was trying to take a shortcut, and then I didn't. Okay. Still not getting the same answer I got there.
Yeah, no, it's not 98.
No.
I did times 12.
Well, times 10.
Because it's 12 meters. See, that's okay. I really need to get some sleep, guys. My coffee is just not cutting it. Nobody caught the mistake I made here. 9 is times 12. Then divided by 1/2. Okay, so there's all my mistakes right there. Okay, so, and I get to record them and post them all. 9.8, so 9.81 times 12. Okay, and then times 2. All right, so there we go, 15.3 meters per second. All right, everybody okay with that besides all the mistakes I made?
Yes.
Okay, how many people have done number 12?
No.
Okay, so number 12, it's actually the reverse. Okay, this time it's saying here's how fast they're going at ground level, but now they're moving upwards. The only way to move upwards is to do work on the floor and have it push you up. Okay, and so, or in this case, the trampoline, so that's what they're doing. They're pushing off the trampoline and going up into the air. Okay, when they're at their maximum height, how fast are they moving? 0. When you're at your maximum height, your speed is 0 because that's where you stop. Okay, you're moving upwards, 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 stopping and then coming back down. Okay, so at your maximum height, your speed is 0. Right, that's what you need in order to kind of get 12 started. So, on number 12, we are initially on the ground. So this is one of those trampolines that's actually like ground level and there's like a hole underneath it. Okay? One of the ones that's in your backyard. Okay? Like one of the Olympic ones that they're built into the floor. Okay? So, we want to expand out our law of conservation of energy here to say that EP initial plus EK initial equals EP final plus EK final. All right, now this is where that context comes into play. Initially, I'm at ground level. So what's my initial height? Okay, that means I don't have any initial potential energy. At the end of this, I'm at my maximum height. And at my maximum height, how fast am I moving? 0. Right, so I don't have any final kinetic energy this time. Okay, now I can set these two things equal to each other, which is what I said all along. The initial mechanical is just all kinetic. The final mechanical is all potential. So 1/2 mvi squared equals m times g times hf. And I'm solving for the final height of the child. So I'm just going to divide both sides by mg. And when I do that, the mass cancels. Now, do you have to cancel the mass? No, it's given to you in the question. Okay, but would it be possible for me to give you a question like this and not give you the mass? Yeah? Okay, it really messes with people when I do that because they think I haven't given them enough information. And I have, as long as they recognize mass cancels. Okay, if it doesn't, you can plug in whatever number you want and it'll still work because it doesn't matter. Okay, I once did that on a unit exam. I didn't put the mass on the question and people kept coming up to ask me what the mass was and I kept giving different numbers. Oh. Yeah, so the first person came up like, how heavy is this roller coaster? I don't know, 2 kilograms? And they're like, isn't that a little light? I don't know. Went and sat back down. Next person came up, how heavy is the roller coaster? 1,000,000 kilograms. Isn't that kind of big? I don't know. And go sit down. Meanwhile, there's people chuckling because they recognize the mass doesn't matter and I'm just messing with you people. Okay? I mean, you didn't need it. I could give you whatever number I want and you'll still get the right answer. Okay? That was the ironic part of it was I was sort of being mean, but at the same time giving the number that would work. Because I give whatever number I wanted and it would work. Okay? All right. So for this one here, now that I've got that, I can solve for HF. So that'll be 1/2 times the speed, which was 1.6 squared, divided by 9.81. That gives me HF, which is 0.13 meters. So they didn't jump very high, like that. Okay? But it's a little kid. Like they're not going to jump very high. All right.
Okay.
Everybody okay with how that one works?
Yes.
Yes? Okay, good. All right. So we talked about this example here already with the bow and arrow. Okay, important that we remember that work energy theorem and law of conservation of energy work together. Okay. Now, if I'm looking at this situation here with a pulley, okay, so this is a system. A system has many parts. Okay, those parts are connected somehow. So these two boxes are connected by a rope over the pulley. Okay. Right now, does this system have mechanical energy? Yes. Why does it have mechanical energy?
The 2 kilogram one is pulling down on the 1 kilogram one.
Right. The 2 kilogram object is higher than the 1 kilogram object. So when it falls, it's going to fall downwards and the 1 kilogram object is going to move Okay, what's going to happen to the energy of this system when I let it go?
Well, it's going to start with more potential. It has kinetic. It's going to have it.
Okay, I'm getting like a lot of different answers here. But the answer is, energy is going to move from one place to another in the system, but the total energy of the system is going to stay the same. Okay? So right now, the 1 kilogram mass basically has no mechanical energy. It's got no potential because it's at the lower point. It's not moving, so it doesn't have any kinetic, but the 2 kilogram mass is above the bottom. So it does have potential energy. When it falls, as it falls, it'll gain kinetic energy. But not all of its potential energy is going to turn into kinetic energy for itself. Some of it is going to be used to do work on this one and change its kinetic energy. So whatever energy the 2 kilogram box loses, the 1 kilogram box will gain, and the energy of the system will remain the same. Okay?
But then, when the 2 kilogram is on the floor and the 1 kilogram is up,
Yeah.
how
Nothing
does,
can happen.
yeah, so then where does all the energy go in the ideal?
Well, if I had it set up that way initially, there would be no energy in the system
Okay,
because it has no potential to do anything,
okay.
right? If
Well,
the 2
then it doesn't
kilogram,
work on
but if the 2 kilogram mass is sitting on the floor,
the- Yeah,
then the system can't move.
yeah,
Even though the 1 kilogram mass is suspended,
yeah.
it can't do any work on the system because the system has no potential to move.
Yeah.
Does that make sense? Okay, but if I reverse it, okay, the 1 kilogram mass can sit on a table, but I let go of that 2 kilogram mass and the system will move.
Okay.
Okay? And it'll move until the 2 kilogram mass hits the table. Then we're talking about converting energy into different forms. Sound, heat, destruction of the pulley, if the 1 kilogram mass hits it, and whatever. Okay? Okay, so. Oh, we've already done. Okay. We don't need to do number 13 because we've looked at that already. Okay, pendulum. What's a pendulum? Right, it swings back and forth. Okay, in the world of budget cuts, this is what we have. We have ghetto physics. Okay? Tell your MLA that there needs to be more money in education because your teacher has a pendulum made out of the drawstring from his hoodie and a piece of athletic tape or a roll of athletic tape that he found. Okay? It's dire. I'm telling you, it's dire, man. There's no money in education. Okay, so it's back and forth, back and forth. Okay, so that's a pendulum. I'm not trying to hypnotize anybody. Okay, no one's gonna cluck like a chicken or anything. Come on, that was the opportunity. Somebody was supposed to cluck like a chicken. Okay, so it's just gonna swing back and forth. Now, when the pendulum is swinging back and forth, the only reason the pendulum swings back and forth is because I pull it up over here. What have I done?
Done work.
Work, exactly. I've put energy, what kind? Potential, and thus mechanical, into the system. Okay? I've given this system mechanical energy in the form of gravitational potential energy. When I release it, the pendulum converts that potential energy into kinetic. So where does it have the most kinetic energy then? Right, at the lowest point in swing. Okay? And then it converts that kinetic into potential on the other side. It just keeps going back and forth, back and forth. If this was a perfect pendulum, it would swing forever. Okay? Since it's not a perfect pendulum, it doesn't take long for it to stop. Okay? There's a lot of friction here at the pivot point. Okay? Plus I was kind of braking it also to make it stop faster. Okay? But yeah, it's going to slow down and stop in the real world. In the perfect physical world, it'll swing forever. Okay? So, here's what I want you guys to try. It's a 500-gram metal ball suspended on a 50-centimeter string. The ball is pulled horizontally and up a total vertical distance of 10 centimeters. It is then released. At the bottom of the arc, the mechanical energy of the ball was determined to be 0.491 joules. What was the speed of the ball at the bottom of its arc?
Could you do that in like the chamber and then it'd go forever?
No. You'd have to have the pivot point at the top be frictionless as well. You wouldn't. There's no way to eliminate it. Yeah. No way to eliminate the friction. But you can get close. Like there's pendulums in like Smithsonian. Okay. Give this one a try here, guys.